Okay, let's talk about generics and solid principles and how generics tie into this. Now, when you get an interview, you're probably going to be asked about this. You're going to be asked, what are generics? And separately, you'll be asked, what are solid principles? What they really want you to do is tie them in together because when you're dealing with enterprise level projects, there are a lot of issues with regard to maintainability and solid principles. So let's talk about this. All right. So, first of all, let's talk about what are generics. Generics just they're just features that allow you to write code that's flexible, reusable, and in a nutshell, one function can accept um, an input type of array and an input type of, I'm sorry, of integer and an input type of string and handle them similarly. For example, I'm going to make a very simple example. You might have a function that allows you to uh, add, right? Add numbers, right? Instead of recreating a function that concatenates strings, or maybe you might have character strings with characters with numeric characters. So instead of just creating a whole different function that will handle the strings that have numeric characters, what you can do is have one function that accepts the integers and the strings with numeric characters and figures out how to add them regardless of what type it is, right? And so that's what generics allow you to do. And so that function, that adding functionality, you're not rewriting it, right? It's all within the function that handles a generic type. And why generics matter? Because they prevent duplication, increase usability, ensure type safety. They align directly with key solid principles, making your code more robust and easier to maintain. Um, the general basics. So this is what a generic function will look like, basically. And I have a function, print array. This function, when implemented, will allow you to um, it accepts an array, and it can be an array of integer or string. But regardless of what type you pass to the item's parameter, it will print the items, as opposed to, again, creating two functions that do two separate things. Okay. Again, generics eliminate code duplication, improve flexibility and scalability. Okay. So let's talk about generics and solid principles and how generics fit into solid principles. Generics help ensure each function or class has a single responsibility by enabling reusable, focused implementations. So now in this situation, we have a class that has data store, right? And that's so basically, and what we're going to do is we're going to append particular types of items into the array called items. Now, instead of saying int right here, we say t. T is a generic type. But in the end, when we implement this, we'll be able to pass to the add function. We'll be able to pass it either an integer or a string. It won't matter. Open close principle. Generic functions and types are open to for extension, but closed for modification. And I'm going to explain that later on in another video. You can extend the functionality to work with additional types without modifying the existing code. And then there's Liskov's substitution principle. Generic types can work seamlessly with subtypes or different types, ensuring objects of a superclass or protocol can be replaced with subclasses without breaking the functionality. Again, I'll make a video dealing with that. Then there's an interface segregation principle. By using generics, you can create specific type-safe protocols or interfaces, ensuring clients depend only on what they need. Okay, dependency inversion principle. Generics allow high-level modules to depend on abstractions instead of specific implementations. Okay, and again, we're going to get into this in the examples that I show you. Okay, now let's talk about associated types and type alias, because these are important when we talk about generics. So an associated type is a placeholder used with a protocol. It's used specifically in a protocol, not in a struct or a class, okay? And the placeholder refers to, it's an abstract reference to a concrete type that's going to be in the class or struct that implements the protocol. Okay. Now you say, what? Again, we're going to talk more about protocols later on. Protocols are merely um, protocols are objects that you use, or it's functionality that you use to enforce a rule set on a struct or a class. For example, if I implement, say I have an object called car, and I implement automobile or vehicle, all my car objects will have to implement everything that I have in the protocol. So if I say wheels, if I have a function called wheels, I have a function called drive, if I have a properties called tires, and I have another property called tire count, every place where I implement, when I implement this protocol, which I'll show you how to do that, all those objects must have those functions and properties, right? Again, this is for mainly for convention, but as we move further and further, it's also used for the practical purpose of testing, scalability, maintainability, and adhering to solid principles. But we will get into examples of that later on. Okay. Now, a type alias is just an alternative name for an existing type, right? And that includes custom types. It's primarily used to improve readability. Now remember, type alias can be used in a struct or a class and within a protocol, whereas associated types, they refer to an abstract type, right? Or it's an abstract reference to a concrete type, right? And they are only within the protocol. Okay, so let's talk about the differences. Associated types, they're used within protocols as placeholders to define generic behavior. Type aliases, they're used in protocol structs and classes. They create alternative names for existing types. So let's get into some practical applications and practical examples of generics. We're going to walk through the code. So let's look at this top, um, this right here. It's called print array, this function. And basically, what I'm doing is I'm accepting an array of strings. But as you can see, I don't specify right here whether this is a string or whether it's an integer, right? I just have an array of T, a generic array. That's it. This is the most simple. I mean, in other functions, what I'll probably have to do is add a protocol, equatable, comparable, or whatever, and use that. But for this is just the most basic example. And as you can see, as I run this, and you go down here, there is a list of strings. Okay. And now I can go here and make this a list of integers. It's very same function. Very same function. Run it. Now it's a list, it prints the list of integers, right? So I don't have any issues with types. Now let's take us a step further. We're going to use a class, right? So let me go ahead. I'm going to comment this function out right now. Actually, I'm just going to comment out the implementation so that and what I did was now I have to, when in my function, I have to denote what data type is using, but it's the same. This class accepts generic types. Items is of type generic. And when I instantiate the data store object, I say string so that it knows what I'm adding to this item's private var. And when I run this and get all, and this is taking a little long. I'm gonna edit the waiting out. Come on, let's go. Come on, you're killing me. There we go. So get all, and now when I look here, see, cat and dog have been added. And you know something? If I want to redo this, I can make this integer, right? And make this item 3, right? Right? And 4. Okay. Now I run this, get all, and let's see what all elements 3 and 4, right? So that's the array that it returns. Okay. So now let's this right here. And I'm going to comment this implementation out. And let's look at this. Right here, we're using the dependency inversion principle. So I'm not going to get super in depth with um, dependency inversion principle. I'm going to say this. Dependency inversion principle is what we use when we use generics and protocols to prevent our code from being tightly coupled. Tightly coupled just means that you change one thing and everything breaks, right? That's technically what it means. So what you want to do is you want to be able to make changes to certain parts and be able to swap out the parts without the whole thing breaking. And that's what the dependency inversion principle does. Now I want you to take this code, take it, run it in your playground, and you need to look at it. We will return to this dependency inversion principle later. But for now, I don't want to overwhelm you with too much. Okay? So that's it for now. The code for this is in a text file. Take it, put it on your playground, run it, try to understand it. Go back, look at the notes that I put in the course, and on to the next.